Well, thank you. And I'm going to have to modulate my voice here so it doesn't blow my eardrums out. It's pretty loud. Um, well, thank you. And I'm going to be talking today about taking the model for prediction across scales, which is a meteorological research model that's global in scale, and optimizing it on NVIDIA GPUs using OpenACC. And my talk is in front of a technical talk that will be given by Dr. Kumar, who works at the National Center for Atmospheric Research as well. And my talk is going to set some background as to how we built this partnership and our motivations for trying to do this, and to give you a sense of all the moving parts and how they work. So I will go first to what MPAS looks like when it's running, if it's running. Okay, and this is not satellite data or imagery. This is model output from a 4-kilometer global model that was done by a postdoc at NCAR by the name of Falco Jute in the mesoscale modeling laboratory. And at 4 kilometers, what do we get? We start to resolve cloud systems. You know, we can see an eye in that particular tropical cyclone. You can't resolve those things. They're rather small compared physically to the size of the Earth. So we have to get down to that few kilometers to really get realistic clouds. This is just a beautiful simulation that gives you a sense of what we're trying to achieve on a routine basis. What this simulation doesn't show you is the pain and anguish that went into actually building this thing. When we ran this model, the output and the analysis and post-processing of the data and the integration rate that could actually be achieved to produce this were such that it was a kind of hero project, and not something that we really feel comfortable running, let's say, in production all the time. So it just gives you an aspirational goal of what we're trying to accomplish. I like this video because it's a 2012 outbreak of tropical cyclones, especially in the Indian Ocean. That's a test case for people doing that kind of research. And as we know from this fall, tropical cyclones are a pretty serious business for the United States as well. We've had a couple $100 billion worth of damage from those. So doing a better job in predicting and understanding their formation and birth and death is an important scientific goal. So until about 3 years ago, NCAR had really no GPU engagement activities per se. There was a little bit of work being done on WRF, but as far as the climate and global modeling community was concerned, GPUs were really not applicable. And I started with a summer project. We had actually 2 or 3 summer projects of this kind, where we worked with students on trying to take some simple numerical algorithms and figure out how they perform on GPUs. And our methodology that we established then was to look at basically 3 things that were roughly contemporaneous with one another when we started, and that was the Broadwell, which was the Xeon that's ended up in our Cheyenne supercomputing system, the Knights Landing Xeon Phi, and the NVIDIA Tesla P100. And so what we really wanted to understand is how well can we perform with a single code across all 3 of those platforms. So really, we started out trying to get performance portability. Now, NCAR builds community models, and they could be run anywhere, so we cannot really just build a model that will run on a single architecture. We try to support the whole gamut of things that are out there. So performance portability is very important to us. Now, We started with a numerical method that was being experimented with at NCAR called the radial basis functions. And radial basis functions are a mesh-free method in which you can calculate partial differential equations. And in our business, we have a standard two-dimensional test case we call the shallow water equations, because the Earth basically looks like a very thin layer of atmosphere on a great big rock. So when you look at what a derivative calculation looks like, it's just a fairly typical stencil that you would get if you choose a set of points. The nice thing about the method, though, is you can choose whatever set of points you want. In this problem, they were icosahedral grid points. So this radial basis function method has some really nice numerical properties I won't go into, but we ended up doing an experiment with that code that compared Broadwell, Knight's Landing, and P100 at different problem sizes. So the number of points you're working with gets bigger as you go to the right here, and the gigaflops achieved on one device goes up in this plot. And one of the nice things about this is that we had a single code generate all this data, and what it gave us was a nice agreement with what you would predict from the computational intensity of the roofline diagram. And so if you look at Xeon Phi, and the P100, those lines represent what the roofline would say is sort of the theoretical maximum, what you should expect from the memory bandwidth. And the interesting thing as well, it's going faster than the theoretical maximum, but for small enough problem sizes, the Broadwell does this typical thing that you see in cached microprocessors, that if the problem will fit into cache, you actually get the cache bandwidth, not so much the bandwidth out of the main memory is dominating it. And once the problem gets big enough, then it comes down like that. Now, it's an indirect addressing problem. So when you do that kind of problem, you don't expect to really get great performance, but we managed to get vectorization out of the problem. Since Haswell, there's been vectorizing indirect addressing on the Xeons. So given the available memory bandwidth, we felt like, well, you can get more or less what you expect out of the hardware with OpenACC. I should mention that. OpenACC directives are giving basically everything that the application has to give. So this was very encouraging. And I won't go into that, but moving along, this fed into an alliance that we called the Weather and Climate Alliance, which is WACA, and I won't go into too much of what WACA, where its origins, but if you think about optimization as a game of whack-a-mole, where you're constantly knocking down the next thing, which is the problem, that's actually the origin of it. But this became initially a partnership just between NCAR, the University of Wyoming, and NVIDIA, and we started out with the objective of saying, hey, if we can do this for a numerical method in 2 dimensions, that's kind of a simple problem, but let's try to find a target that looks more like a real scientific application. So he said, okay, we'll try to go after the dynamical core, or the PDE solver, in the model for prediction across scales. That's about 10,000 lines of code, and to compare that with the RBFFD, I think the RBFFD code in the right-hand side evaluation would fit on a page, right? So it's rather simple, but we tried to go for this 10,000 line code. So we had this idea that we were going to let me move along here. One of the things that we used was the kernel generator. So kernel generator is a tool that we have for building on the fly unit tests from a big complicated model so we can break it down. So this was very useful in taking something on the order of 8 kernels inside those 10,000 lines and breaking them down into tractable pieces which could then be optimized. Okay. So this is just to give you a sense of how big the relationship between this project in these different institutions. What we've got is roughly, I think, 14 people, and after we got started on MPAS, we realized that KISTI was also interested in MPAS, and so we had a decision that we were going to split up MPAS, and we would just focus on this dynamics, and KISTI would focus on the physics while we messed around with the dynamics. And this is me doing a bunch of, logos. Now, one of the other things that after we got that code in hand, and Raghu Kumar will show you some of the performance results, but we got very encouraging performance results from the single device activities. And he will basically tell you it's about one P100 was equivalent to about 2.5 nodes of a Broadwell. And so another way to say that is that a single Broadwell node is about 2.5 times slower than a single P100 device, solving the PDE solver part of the code. And so when you go and you say, well, that was great, you got the dynamical core ported, now you want to do the physics, what does that look like? What do you have to do? In the physics, one of the things that's caused people to stymie and stall out when they're going through the code is the fact that there's a lot of traffic over the PCIe bus between the physics you have imported and the physics you have ported. And when you're grinding through that physics, making sure that you haven't made a mistake and caused the answers to change can be a real problem. So in talking to IBM about this thing, I said, it would be really nice with the NumaLink that we would have this, this high-speed interconnect that would allow us to effectively reduce the overhead on the code, and that would actually improve our speed. And a way to think about this is just in terms of return on investment as a function of time. And the real problem with GPUs is that it's a U-shaped return on investment, right? I mean, I slow my code down while I'm doing the physics part, and executives don't like U-shaped return on investment curves. So the idea was, well, that's where you get to break even. That's sometime in the distant future. And you would like to have a return on investment curve that was much shallower and much earlier. And the problem with the other curve is it looks a lot like failure, because out here, if you never get back to break even, then you really haven't succeeded. So people don't like that. So with the IBM system, we had this idea. It would slow down less. We would have uniform memory access, so that we would essentially have the migration of data from the front end to the back end accelerator be much faster and transparent from the unified memory point of view. So I really would look at that as an optimization and not a correctness issue. So, that's the technical part of this. The NVLink is giving you that bandwidth, and the unified memory programming model gives you the transparency that you need to do that. And so this is kind of the partnership that we started out with. There's a picture of some of the students. I apologize, I don't have some of the newer students in there. These are students at the University of Wyoming that are actually doing the work. And, you know, looking at that arrangement again in the system, having the 80 gigabytes a second is very, very helpful. And again, that high bandwidth link, I think everybody probably knows about NVLink, but it makes the superior performance of that is going to make it a lot easier for us to migrate the physics over. And I already talked about that. So adding IBM is sort of turns this into a baseball diamond, where we all can do our individual pieces of this. Right now, we have moved the code over to the P92 cluster at IBM, and we are starting the process of incrementally improving the GPU's pieces, putting the GPU pieces that have been accelerated into the IBM system. So, so when we push on in this phase 2, there are a couple of nuances on this. One is when we're done, the PDE solver, nearly all of the physics will be moved over. So this is sort of the steps as we go through. One of the issues is I/O. I/O, we're going to try and use a library called CyanLib from the Research Center in Jülich to provide high bandwidth I/O for the system. And the other thing we're going to do is keep some of the physics overlapped, or the parts of it that are not amenable to being ported to GPUs running on the front end. So there are two pieces there. One's the radiation, and one is the land surface model, which is full of branchy code. So you can think about this as for a 6 GPU system, you will have a process that's dedicated to MPI and MPI-I/O. It will have a share of the threads available to it, which is what this sort of 4 screen represents. And as the model's integrating, the radiation will calculate the radiation in a lagged fashion, so it will be out of phase with the dynamics, and then that the forcing from the radiation will be passed to the GPUs every few time steps to update that. So, if you're running at 4 kilometers, you have a very short time step, and the radiative transport properties of the atmosphere are not changing very fast. And this is a picture of what that looks like. So the yellow boxes are the radiation at the start of the simulation, and they run lagged by, in this case, 5 time steps, and then their values are broadcast to the rest of the model, which is integrating from time step 1 here to time step 18, and then every 5 time steps, information is passed back to the radiation, where it picks the data up again and runs that simulation, and then passes these forward as the model moves forward. So in this way, if you do it right, we expect the radiation to be roughly balanced with the execution of the time steps. So we can control how often we call the yellow boxes and how far out of phase the yellow boxes are. Okay, so I think I will leave I'm really trying very hard not to give you any performance results. And the reason for that is because I am trying to be a teaser for the next speaker who will do the performance results. And I've already said that he gets about 2.5 times a Broadwell from a P100, and you probably can do the math about what a V100 would do for that, which is even better. So I guess I will take a few questions about the partnership and the strategy for migrating MPAS over to GPUs, and then the next speaker can talk about performance. Thank you.